and we're talking about specifically today single and double replacement. Okay, single and double replacement lend to the net ionic equations way more than synthesis, decomposition, and combustion. In fact, if we take a quick look at combustion, right? Combustion, it's a liquid or a gas over here for your starting material, gas for oxygen, gas for CO2, and either a gas or a liquid for H2O. Nothing will split. Combustion does not do net ionic. You just do the CO2 and the H2O. Occasionally back here, you will get net ionics. So if you look, I said we're going to go back and fill this in, and you can do this now. So if you look at this page, all right. Oh, I got to get rid of the stuff on the bottom. I keep forgetting that. Come back here. So remember when we made the base over here, where we said metal oxides in water form a base? Well, you now, when you form that base, have to ask, is the base strong or weak? This is where one place where you do net ionics. Because if it's strong, then it splits. So we made sodium hydroxide that first time, and that's a strong base. So when we get to the end, we have to take this molecular right here, and we go one step further and just rewrite it with this thing splitting. These do not split because they're solids and liquid. It's kind of silly. It looks like it's like, why are we doing it? Because in actuality, they don't stay together. If you put sodium into water, you make sodium hydroxide, and sodium hydroxide ions like to be dissociated with other water molecules around, so it splits. Okay, now this is kind of a caveat where you say, well, this will split up into CO2 and water, so we don't do anything with it. And then the other one, this stays a solid, so we don't have to worry about the phases. I'm trying to remember which other one we have to worry about over here. With decomp, it is, where is my hydrogen peroxide one? Here it is. This is the one you have to worry about. And it's the only one out of decomp. If H2O2 is an AQ, that will actually have to be written as 2H plus 1 O2 minus in AQ, and you have to split them. No, actually it's N minus 2 AQ. That's the only one. And then of course on the other side, this is liquid, so it's not going to split, and this is a gas, it's not going to split. So what you're only doing is you're just taking the first part and splitting it into the ions. Okay, so that's the only time back in synthesis and decomp you worry about this splitting thing. Oops, I have another one here. Come in. There we go. Alright, so single replacement net ionic reactions. Steps, until you get used to this, until you can see in your brain what's going to happen ahead of time, you're going to write it out in steps. So step 1 is going to be to write a molecular equation. And then I'll usually say balance that molecular equation. And then see what splits and rewrite with ions. Whoops. What splits. And then 4 is rewrite with ions. Then you're going to see, does anything cancel? It's a process. It'll become automatic after you do it a while. So we talked about magnesium before being added into iron 3 chloride. And then You swap places because in AP we say they always work. Then you write out the rest of the molecular equation by rewriting the formulas. Okay, so that's the other thing, is always rewrite formulas on product side. Do not carry over subscripts. Okay, rewrite the formula. So the synthesis, where we add sodium into water. I shouldn't say it's synthesis, single replacement, sorry. It's the S's over here. The sodium replaces the H plus because the H plus is positive. So you get an H plus come out, but you have to be careful over here because it's diatomic. Then you have to go back and balance. So you make a base plus a gas. We can take a metal and add it to acid. That's a very common, this is common, very common single replacement. And the other thing too, guys, about these reactions are called redox reactions. It's a new word that is called an oxidation reaction, oxidation reduction. These are redox reactions. All single replacements end up with redox. This is one place where I differ in when and how I teach things. AP expects you to learn all of redox right now. And I save redox to the end because redox also has to do with a lot of conservation of charge, which we haven't learned yet. It has to do with cells. It has to do with spontaneity. It has to do with activity. So we don't learn the thermodynamics till later. So redox plays off of thermodynamics. So I teach you redox at the end. Okay, so all single replacements are redox. Doesn't matter what happens in this single replacement. This is called oxidation and reduction. Oops, I can't spell. Just to get you used to those terms. Electrons flow, because this goes from a 0 charge to a +1 charge. It's changed its number of electrons. This goes from a +1 charge to a 0 charge. It's changed its number of electrons. We'll learn more about that later, but I want to get you started thinking about it in the back of your head. So again, this one is a metal into any acid. That metal will kick out the H plus, and then your H plus will turn into H2, but this turns into net ionic, and that's what's difficult. In this one, because it splits, your chlorine ions can get canceled out, right? And then on the other side, this is where you have, and we call this an anion replacement because it's the negative side. Up above was a cation replacement, right? This is a cation because it is the positive. I'm going to go through a couple coming up. We'll go to the next page. I'm going to do some that I didn't do yet. So we're going to go through the process. Zinc pellets. Okay, so zinc pellets, that's going to be a solid, is added to sulfuric acid. So you have to know OH plus sulfuric sulfate. So I'm going to have to make a reaction there. I'm going to have the zinc kick out. the H's. Now this is why I say to you, after a while you're going to go, I know what's going to split and not split. Okay, most sulfates are not soluble, except, let's go back. Here's sulfates. So most most sulfates are soluble, except with strontium, barium, and lead. Those are the ones we look for, and mercury. But if I look at my list, zinc is not on that list. So zinc will be soluble. Oh yeah, silly me. I started writing and then I crossed it out. Okay. So that means, and I'll start over here. I know you have it in a different place. But that was a solid. We added it to this. We said this is going to come together. And then we're going to have H2 gas going off. Right now, I got to make my formula here. But now we have to ask, does anything split? Well, this will not. So this stays together. But this, which is AQ, will, because this is a strong acid. So it splits. This is soluble. It splits. So this is the molecular. But we have to write net ionic. So to write the net ionic, we split the ions apart. Now notice, this is a subscript for the H. It comes out in front as a coefficient when you split it. Okay, this will not split because it's a gas. So what is in common? This is in common. That's the only thing that splits away. Please understand, okay, this has no charge. This is a 2 plus. These are two different things. You cannot cancel them out. This is a +1. This has no charge. They're two different things they cannot cancel out. So my net ionic for this, and that's why I said sooner or later, you will have intuition. And you will know, oh, my sulfates are the only things that are going to cancel out. And you might say, no, I'm never going to do that. You will. And I have to go back and make sure these are AQ to tell the reader they were in solution and they split away and this was solid. Okay, that's a single replacement. Okay, you can do that for lots of different situations. I can do another one. I'm going to do a negative one. Iodine crystals. Well, iodine, diatomic, plus sodium chloride. Okay, iodine's going to kick out the chlorine. So I'm going to get sodium with the iodine, and I'm going to get chlorine out. Be careful. Do not carry that over. This is +1. This is -1. So the actual formula is NaI. Alright. Now, chlorine, we got to think. Monatomic or diatomic? Ooh, this is diatomic. And this will be given off as a gas. This will most likely be a solid. Could be a gas, but it's most likely solid. This was a crystal, so that's a solid. Right? And then this was an AQ. Oh, sorry, if that was AQ, I forgot. This will be AQ. Now, we have to think, does anything split? Well, this will split. This will split, because group 1 metal. So if I split them, I'll write it next to it. I have iodine and the diatomic, Na plus Cl minus gives Na plus I minus, plus Cl2. And you go, does anything split? Yep, these split. Okay, so now I have I2 plus Cl minus, but I'm going to have to balance. I minus plus Cl2 minus, Cl2, but we have to balance them. I need a 2 in front of here and a 2 in front of there. And that's an anionic replacement. Double replacement has some rules to it. I mentioned the other night that you have to have conditions that have to be met. And you have to meet at least one of them. Could more than one of them be met? Yes. That's what kind of makes it confusing. So one of these has to be met. We either have to use our solubility rules and figure out something that's dropped out of solution. And that's why they call it a PPT, a precipitate. Because just like snow falls, so do these little crystals. You get these crystals that look like little flakes falling, so they call it a precipitate. Now, double replacement reactions are not reversible reactions. They are not redox. Nothing changes charge. Okay, if they are reversible, it's because you have ions that don't split. But most likely, if a double replacement reaction happens, it is not reversible. That's why we say, they go to completion. They always go to completion. You can't go backwards. Now, there's some stipulations. Okay, these are the conditions. You form a precipitate that is based on your solubility chart. Or you form a gas. So again, this is the tough part. If you see these things as products, you have to say, oh yes, they form a gas. And on top of it, these ones decompose. So you don't leave it as this. It doesn't stay this way. You have to rewrite as these over here. So you got to take it a step further. And that's why double replacement gets confusing. Okay? So this is like memorization. You got to commit it to memory. And then just to go over the very bottom. And then I'm going to do a couple examples for you. Why did I cut it there? Huh. I'm going to get rid of that. I asked for full screen snip and it went backwards. There we go. Okay. So, that's not doing what I wanted to do. Sorry, that was my bad. I went too far up. Now I can see it. All right, molecular species. Water is a molecular species. What you will find, water is always formed when we do these things called a neutralization reaction. We'll study neutralization reactions in acid-base chemistry, because when you add an acid to a base, you get a neutralization reaction. Neutralization reactions are always double replacements, just a subset, very specialized one. Now, if you form any of these things, a weak acid, a weak base, or an insoluble salt, the reaction goes. Insoluble salts, again, are considered PPTs. So it's kind of being redundant. Let's look at some. Now, this is where formula writing comes into place. Big time. I have silver nitrate. All nitrates are soluble. So I have to think silver plus 1. Nitrate, NO3 minus 1. Potassium plus 1. Chromate, CrO4, 2 minus. Okay. I'm going to swap ions. These two will swap. I will get K plus NO3 minus plus Ag plus CrO4 minus. Now we have to do things like solubility rules. Oh, all nitrates are soluble. All the group 1s are soluble. So both of these will split on the left-hand side. On the right-hand side, all nitrates and all group 1s are soluble. So, since we say all AP reactions go, that must mean this guy has to be the solid. Okay, if I were to write this formula, it's Ag2CrO4, and then if this is the solid, this is the net reaction. So we go backwards. What makes this up? 2 Ags that were aqueous plus 1 chromate. I think I have the right charge on chromate. Should be 2 minus. And this is my net ionic double replacement reaction. Okay, I skipped a step. What did I skip as a step? Was writing a balanced molecular. And the reason why I skipped it is I could see, oh, well, yeah, that's going to be balanced that way. Oh, go that way. There we go. I needed 2. I could see before I even, whoops, I did it again. I don't know why I want to right now put a charge up there. Before I even got to this spot, this is my balanced molecular. This is what you would need for regions. But since I have to go breaking up ions anyway, I just might as well go backwards from the thing that's going to be the precipitate. Because everything else, if I do it right, will cancel out. If I split these all out, you see that the nitrate's going to cancel with the nitrate. Potassium's going to cancel with the potassium. Why take the time to write those things out? You got to go at a fast speed. So I tell people, once you know your solubility rules and you can identify this is my product that's going to precipitate, skip doing the molecular. Just go backwards. Now you're going to hate me because we're going to do a lab and I'm going to say do the molecular at one night and then do the net ionic the next night. I'll do one more and then we'll call it quits for this, but then you can do some more. I have ammonium chloride. I am going to add cobalt 2 sulfate. Now I'm going to swap. This is not a good one to change because by solubility rules you wouldn't know a particular one drops out of solution. And actually by solubility rules I don't think either one of these work. Cobalt 2 goes to C2. Cobalt chloride because this is always soluble. So out of this would most likely be the one that would be a solid. So it's not listed. I don't believe it's listed. But we're going to take that one and I'm going to go backwards with it. And these would have AQs next to them. I get lazy and I leave them out. I'd lose points. Let's do this next one, zinc acetate. My arm's touching the mouse pad, so I keep getting these little things going on. Alright, so I have to make my formula for that. I have cesium hydroxide. Group 1 metal. Soluble. Strong. I'm going to switch. I get cesium acetate. And zinc hydroxide. So, all acetates are soluble. All group 1 metals, strong. This is going to split because I got two things, group 1 metal and I got acetate. Which means out of my two products, this is going to be a solid. It's not one of those special ones where you make H2CO3 or ammonium hydroxide. But this has to stay as a solid. So if I look at my formula here, they'll have two. So this is going to be this. So now I just focus on this baby right here and I split it apart. It's zinc 2 plus 2 OH minus ions gives me zinc hydroxide. That's my net ionic equation. And that's it for double replacements.